Okay, so yesterday where we left off, we were talking about electrophiles and nucleophiles. We were starting to see the beginnings of some chemical reactions, talking about homos and lumos. And what we want to do right here is solidify that a little bit and make sure that we're ready to get on to some more challenging details. So let's start briefly by going over those rules that we talked about in that last lecture. So what we're looking for to cause a chemical reaction, especially in context of organic chemistry, is we are looking for a HOMO that is high in energy, and we want that to attack a LUMO that is lower in energy. And so what we're looking for to see an important HOMO, we'll call this an important HOMO is first going to be lone pairs. So lone pair electrons. And then second, we are going to be looking often for pi bonds. So no, this is not necessarily a comprehensive list, but this is going to be a fantastic start here in the beginning of organic chemistry. And especially for the next few lectures, these are what we're going to see, is essentially lone pairs first, and then pi bonds. And so I'll number these as well. It is decently well treated as a ranked list. Next, an important LUMO is first, I'll use numbers here as well. So first, an empty p orbital second, a pi star orbital. And then third is going to be a sigma star orbital between a carbon and we'll call it kind of an interesting atom, often a halogen. So often that X is going to stand in place for something like chlorine or bromine or iodine for those halogens. But we'll see throughout the semester that there can be other things there as well.
Can I interject just briefly there?
Yeah.
I would just say that for number 3, you're looking for sigma stars associated with weak bonds. So sometimes carbon-halogen bonds, carbon-fluorine is actually a really strong bond, but carbon-bromine, chlorine, iodide, those are weak bonds because those atoms are large and the bonds are necessarily long and weaker. So if a sigma bond is weak, that means the sigma star is correspondingly low in energy. So understand you're looking for a reactive part of the molecule, and these sigma stars, most sigma stars are not low in energy. Carbon bonds are generally not weak. Carbon-hydrogen bonds are generally not weak. But you'll start to recognize a ton of bonds that are weak. Many of these involve carbon, chlorine, carbon, bromine in the first part of the course, but you'll see others.
Yeah, thank you. And we'll see an example of that where I will show you that idea where we're looking at sort of these low energy bonds. We'll get that in a bit.
In the problem set, there's an example of a reaction where the nucleophile takes the electrophile at an oxygen-hydrogen sigma star bond instead of a pi bond that's present in the molecule. Why is that?
So let's see. So we have a nucleophile attacking the sigma star of an oxygen-hydrogen bond. That's what we're seeing. So I'm trying to remember the exact question.
It's probably a carboxylic acid.
Probably.
And we can deal with that example in just a little bit.
Yeah. Okay. Then there's another hand.
So it doesn't have to be right now, but I was curious about the MTP orbital, like what it looks like.
Yeah.
I know it's not common, but I haven't seen a lot of examples of it.
Yeah, we're going to see that next. That's going to be the first example that we look at. So the question was, what does an empty p orbital look like? Because, yeah, that's not something that we've seen very often. In Chem 105, 106, that's an unknown idea, having these empty orbitals, these, anions, these cations, these weird atoms that can have these empty orbitals. We will get to that in great detail. And in fact, to the point where that's not very common, they're actually incredibly common, which we will see through the semester. So hold tight for about 5 minutes and we will answer, what those look like very fully. Okay. So the first thing that I do want to do then, really what I want to finish up before I turn the time back over to Dr. Price, is I want to give examples of essentially everything on this list. I don't want anything on here to be an unknown, kind of just a vague idea. I want you to have something to point to, when you're doing your homework, your problem sets on your exams, you have something to point to. It's like, oh, I've seen that before. So we're going to look at some reactions, and we're going to learn details of all of these reactions throughout the semester. Everything that we're showing here will have essentially a dedicated chapter to it. But like I said last time, we're essentially spoiling the entire semester with this idea of nucleophiles attacking electrophiles, and I want you to see that here. So the first thing that we will do then is let's start with an empty p orbital. So one example of an empty p orbital that we will see plenty of in the coming chapters is something that takes this form, where we have a carbon with only 3 bonds. So this isn't a carbon with a double bond, it's a carbon with 3 single bonds and nothing else. This is something that we call a carbocation. And what this has to, make it work in its, interesting chemical ways is it has an empty p orbital. Oftentimes, this is a result of some previous chemistry. You've done something to perhaps rip off one of the bonds on the carbon, and you've left that carbon alone to just have this p orbital just sitting in place, waiting to do something.
And the carbon should have a charge on it, right?
It should have a charge on it. And so again, as I said, a carbocation. So we have this empty p orbital. It's got nothing going on. If we looked at its molecular orbital diagram very roughly, we'd see that there are 3 sigma bonds, or 3 CH sigma orbitals. And then there is that empty p orbital right at that break-even point. Let me move that, better board management. There's those sigma star orbitals. And if we populate our electrons, we have 6 total. It's 2 from each bond. So 1, 2, 3, 4, 5, 6. And that p orbital is sitting there empty. Yeah? Do all empty orbitals fall on the break-even point? For simple contexts, yes. So s orbitals and p orbitals and d orbitals are all different from each other. Those are going to be all different energies from one another, but for 99.9% of cases, we are just going to make things relative to the remaining p orbitals. Because if anything happens, and by the way, I'll repeat the question. So are p orbitals always on the break-even point? That's what I'm answering. So when an atom creates a bond, the s orbital is always hybridized. We have sp, sp2, sp3. There's not a situation where we'll just have like a p2 hybridized orbital. And so with that, it's fair to call that p orbital essentially that break-even point. Now, there's a whole lot of semantics behind this, and I'm sure Dr. Price is probably cringing at this answer. But for purposes that, as far as this class is going to go, call the p orbitals the break-even point.
And same with the lone pairs, frankly.
Yeah. Yep, lone pairs as well. Yep, call those your break-even point. You know, because what we're doing is we're trying to do chemistry that's trying to make our electrons happier. We want to do something that will make our electrons happier. And so if we just call their default, their native resting place, the break-even point, then, you know, any movement from there helps us predict our chemistry. Okay. Yeah?
Will you ever have an example where you have non-bonding lone pairs and an empty orbital?
Will we ever have an example with non-bonding lone pairs and an empty p orbital? I'm sure with time I could come up with something, but as far as homos and lumos go, those are going to do different things. So your empty p orbitals, that's going to be referring to your LUMO. You know, that's a place where electrons can go. As far as lone pairs go, that's going to be referring to a HOMO, or a potential HOMO. And so, sure, you could have a molecule or an atom that has both an empty p orbital and lone pairs, possibly in some situation, but they're going to be filling different roles. Again, one of them is the HOMO, one of them is the LUMO. So based on what the other chemical is, you can predict still what's going to happen. Because you know, very likely the other chemical will have an important HOMO but a pretty useless LUMO, or something like that. Does that answer that question? Okay. All right. So that's one example of an empty p orbital that we will see plenty of. We're going to see this all the time in some coming chapters. Now, if we wanted to do some chemistry with this, all we need essentially is a molecule or an atom that has an orbital that wants to attack that empty p orbital. So one such example that we will see is chloride. So just Cl minus. So that's chlorine with a full valence shell with 8 electrons. And here we would see that it has 4 hybridized sp3 orbitals. Well, sp3, you know, sigma bonds.
Well, they're not
Or not bonds, lone pairs.
Yeah.
So sigma orbitals. Sorry, I'm kind of in Vesper land a lot of the time. This is MO theory. And if we were to rank these sp3 hybridized orbitals, these non-bonding electrons, are going to sit higher in energy to that p orbital. Meaning that we could see some of these electrons come down and attack that p orbital. So we could see those electrons come in and attack that p orbital, and that would give us a chemical reaction where we would create another bond. So the product of this reaction would be something like this, where we have our 3 hydrogens still attached with a new bond formed to that chlorine. And so on here we see, so on the carbocation, we had a HOMO and a LUMO. And on that chloride, we had a HOMO and a LUMO. But not all of them are created important. So in this carbocation, our HOMO is going to be, you know, some sigma star orbital, but it's not on my list. I don't see any lone pairs. I don't see any pi bonds. So whatever it is, who cares? Who cares what it is? Probably a sigma star. I mean, well, it would be a sigma star, but that doesn't help us do chemistry. As far as the LUMO, though, we see that p orbital. Now for the chloride,
You don't actually mean sigma star, you mean a sigma bonding orbital, sigma star.
yes. Sorry, I will get that right eventually. So now for the chloride, our HOMO, we see that we have a lone pair sitting inside of an sp3 sigma orbital. And then for the LUMO, you know, we've got some stuff, but not really anything that important. So probably just some sigma star orbital. So this is an example where we have only one important HOMO and one important LUMO, and that tells us pretty precisely what our chemistry is going to be. We are going to have our HOMO, our highest occupied orbital, attack the LUMO of the other species. Yeah?
How do you determine that those low pair sp3 orbitals are higher in energy
So good question. So how do we know that the sp3 sigma orbitals are higher in energy than the empty p orbital? So that is a very good question. Really what I would say to that is we don't always know. You know, not every lone pair is going to be able to attack every empty p orbital, for example. That's something that organic chemists have fleshed out over the years of over the speciality. Now that being said, this is why you need to keep coming to lecture beyond today. Even though I've spoiled the rest of the semester, we're going to be learning those semantics and those rules that are going to let us predict these types of things. So right now, the focus should just be on this idea. You know, here's a HOMO, here's a LUMO, and I'm telling you this reaction is going to happen. And so as far as your grade is concerned, when we're getting to exams, quizzes, problem sets, etc., we're going to tell you that a reaction is going to happen. And therefore, here's your list of things to look for. I want to look for an important HOMO and an important LUMO. I was told a reaction will occur, so I know what to look for. Now again, in the future, we will ask you, are these going to be compatible orbitals? But we're not there yet. Yeah?
For the chloride, why is it an sp3 orbital if it's not bonded and it's just not be hybridized, it's just like 3?
Good question. Yeah. So why is this chlorine, why is it not, 3p orbitals? Why is it sp3 hybridized? Very good question. So that's something calling back. All right, Dr. Price will fix that while I answer your question. Thank you. So it's a geometry issue. So remember that steric groups, a steric group meaning lone pairs, bonding atoms, things like that, want to be as far away from each other as possible. If we have 3p orbitals, then everything is stuck at 90 degrees to one another. So let's draw some atom Y. And if it had 3p orbitals, we'd have one there, we'd have one here, and then we'd have one 90 degrees to that on the z-axis. All of those being at 90 degrees to each other. Now this is a little bit of an oversimplification, but let's just put our electrons into those orbitals. Those are at 90 degrees. Those are unhappy electrons. So even if there's not a bond that's being formed, our atoms are still going to hybridize so that it can dump those electrons into better geometries. And so our Y is going to now instead have that tetrahedral geometry that we know and love. And then one going back there, where now it can dump all of those electrons into and be perfectly happy about it. So very good question. Now something like the carbocation, why is that not tetrahedral? Why is that not sp3? That p orbital has no electrons in it. So there's no drive to try and hybridize it, because this trigonal planar geometry has things at 120 degrees, which is much better than the tetrahedral angles of 104, 109-ish, around there. So it depends on sort of population. Are there electrons in my orbitals or not? and that'll determine our geometry. So very good question. Did that answer that?
Yeah.
Okay. All right, so that's the first reaction that we'll see. The next reaction that we'll look at is similar to that question 2. It's going to be using that molecule. So let's look at carbon bonded to, or double bonded to an oxygen, and we're going to add to this OH minus. So what do we expect is going to happen here? So whenever I have something like this, my first thought is essentially, let's find out what the HOMO is and what the LUMO is. So let's actually take 60 seconds, talk with your neighbor. What is the HOMO and what is the LUMO of both of these molecules? Okay, let's come back together here. So hopefully in that 60-ish seconds we got something good. So on this first molecule, so what we have, for a HOMO, we see that we should have a lone pair on this oxygen here. So that likely is going to be our HOMO, is the lone pair. As for the LUMO, we are going to see that we have, let's see on our list, let's scroll back up there, see what it could be. So for LUMOs, we're looking for empty P's, pi stars, or CX sigma stars. In that order, so I see, I don't have any empty p orbitals, but I do have a pi bond. And every pi bond has a pi orbital. Every pi orbital has a corresponding pi star orbital. So that's going to be our LUMO, that CO pi star orbital. Now for the OH minus, what we should have there is we see quite obviously, there's not a lot of other options. I shouldn't say obviously. We're still new to this. The lone pair on the oxygen. And then the LUMO, as for that, I don't really see anything significant. I don't see anything special on the list. So the lowest unoccupied molecular orbital, it's probably some sigma star something, but I don't know. It's not on the list. So now, as for predicting my chemistry, this tells me what's probably going to happen. So the molecule on the left, that's acetone, has both an important HOMO and an important LUMO. But the OH minus only has an important HOMO. So that tells me what I can predict. I can expect my HOMO, the one where the lone special highest occupied molecular orbital, is going to attack a LUMO. So the lone pair on this oxygen is going to attack the pi star on the CO in this case. So what we'll see is just that. This lone pair, one of these lone pairs is going to come in and attack and give us some chemistry here. Yes?
So does the more lone pairs on a molecule mean that it's more likely to be a hole? Because I realize we have lone pairs on both molecules,
Yeah, good question. So the question was, does more lone pairs mean that it's more likely that that's your HOMO? So I will say, and this is probably a really dissatisfying answer, but I'll explain it, is mathematically speaking, yes. That is going to increase the odds of that. If you have more electrons in your lone pair positions, that's less chances for the other important orbitals to show up. Now, we'll see situations where this molecule, where this acetone, even though it has less lone pairs, it can still behave as the HOMO in some reactions. And we'll see that plenty in OChem too. But yeah, the thing is, they're both available. It's available as a HOMO and as a LUMO in that molecule. It depends on the other partner. Yeah?
I'm just going to interject real briefly on that one to say that what Nate is teaching you here is really cool because it's going beyond what's on that quiz out there. If you notice on the quiz out there, for reactions, I'd say this molecule is a nucleophile, which tells you go focus in on what the HOMO is. And this molecule is an electrophile, go focus in on what the LUMO is. And I think one of the questions that's in your minds is, how do I know which one's the nucleophile or the electrophile? We're not quite there yet. We're going to get that, especially in chapter 2. But for now, Nate's giving you a really useful tool, which is if you can't identify an important LUMO, but you can identify an important HOMO, that's probably the nucleophile. If you can't identify an important HOMO, but you can identify an important LUMO, that's probably the electrophile. Now, the acetone that he drew is confusing because it's got both. That shouldn't be surprising. That just tells you this molecule can react in both ways, depending on the situation. Though here, it should be clear because the other partner can only be the nucleophile.
Yeah, thank you. Yeah?
I probably just read it wrong, but I thought I saw in like the study guide in the textbook that the pi star antibonding orbital is higher in energy. It's like above the dotted line from the lone pair. So how does the lone pair go to?
Good question. Very good question. So the question was, pi star orbitals are usually above the break-even point. So why is this reaction happening? So we can give you a straight, full-on answer if we want to do some brute force calculations on the supercomputer. But what we will find is that comparatively speaking, so let me just draw the location of that pi star orbital. So that pi star orbital is going to be here, where for whatever reasons caused by the laws of the universe, the attacking lone pair, that attacking orbital, I'll just draw the one to keep it straight, is going to be higher in energy. Even though it's a sigma bond or a sigma orbital, it's going to find a way where it can relax. Even though it's going into a pi star orbital, it sees a chance that's, to be in a better place. And then what we'll see is, some rearrangements in the molecule, which I will show here now as the product of this reaction. We are going to see some, what we call an addition reaction. So this OH is going to bond. And we are going to attach it in that way. So we're going to turn that pi star, or essentially, very oversimplified, we're going to turn that pi star orbital into a sigma orbital. And that's going to give it a chance to really relax in energy after the fact. So hopefully seeing the product makes that much more clear on why that's favorable. This essentially is the entire idea. Remember back in Chem 105, 106 again, activation energy. That's what we just showed right here. And even if the pi star, so let's even draw it, there's a very good chance that the pi star could be higher in energy. But when it's done with the chemistry, it's going to be in a better place. And so which way it is, I'm not sure, but what I do know is that it ends lower than where it started.
One of the ways you can show that happening,
I'm sorry, is, I feel like I'm like a dad that's like, no, son, let me do it. It's a family tradition. My grandpa was like really old and he wouldn't let my dad do stuff. Like, Tracy, hold the bushes while I do the actual cutting. And my dad's like 50 years old and he's still getting to hold the bushes. So I'm sorry, Nate. I think I just had an idea to illustrate this point. When you combine a HOMO with a LUMO, you get a lower energy in-phase combination and a higher energy out-of-phase combination, and that's your new sigma bond and your new sigma star. And what that means is the electrons in the HOMO get to now be in a bond, and they are lower in energy when they started. It turns out this kind of overlap can happen whether or not the lone pairs start out higher in energy than the pi bond. So it doesn't actually matter whether they're above or below. They need to be close. But if they are close enough, you can get HOMO attacking LUMO, and the product of that is a new sigma bond and a new sigma star. The other thing I wanted you to do is talk about what happens else here, because this is an anti-bonding orbital.
Yeah. Okay, so very good question. Yeah?
Okay, maybe this is a question for you, if not Dr. Price, maybe you want to answer it. So, as I understand it, the closer that the orbitals are in energy, the better the splitting. So you'll have a lower new molecular orbital and a higher new antibond. So is the, like, whether the HOMO is higher or the LUMO is higher, is there a different, like, drop-off how big the splitting is?
Yeah.
Is the splitting worse if the HOMO is like 1 point higher or if the LUMO is 1 point higher? What's the directionality matter there?
Yeah, good question. So the question was, so we know that if two orbitals are close in energy, then the splitting will be more significant, a higher star and a lower bonding orbital. So does it matter if if there is an offset, is it better to have the LUMO higher or the HOMO higher? As far as I understand, it doesn't really matter. Perhaps there's something in the deep doctrine. But if it is there, that's the deep doctrine. And we're we're drinking skim milk. We're not at the meat yet. Yeah?
Can you explain why the oxygen is negative in the product?
Yes, I can. That is the next thing I wanted to talk about. So this pi star orbital, and the question was, why does this oxygen end up negative? So really quickly, let me push an arrow. So we know if we create this bond, if we have that OH bonding right there, we're going to have an angry carbon right here. This carbon right here now has 5 bonds to it. So we need to do something that's going to make that carbon happy. So we're going to push some electrons onto that oxygen. It's going to now have 3 lone pairs, giving it that negative charge. Now, the question that I also want to address along with that is, why did it attack the carbon rather than coming up and attacking the oxygen up there? Because pi star orbitals, they're like, it's on both sides. It could have attacked either of those atoms. So what's going on here? So, yeah?
Oh, no, I was going to answer the question while I was
Oh, okay. So yeah. So with this chemistry that we're seeing, again, a nucleophile, something that loves a nucleus, is attacking an electrophile, something that loves electrons. So we are always looking for something electron-rich attacking something electron-poor. So obviously, something with a negative charge on it, 3 lone pairs, is going to be very electron-rich. Now, here on the acetone, we don't really know. There's a lot of electrons spilling all over the place. But I do remember from Chem 105 that this looks like a polar bond. Oxygen is more electronegative than a carbon. So this is going to be unequal sharing of that bond. And I'm going to end up with a partially negative oxygen and a partially positive carbon. Now, since this is essentially just electrical attraction, I've got a negative charge on this OH minus being attracted to something. I'm going to be attracted to the positive side of this. And that's going to tell me where I'm going to react. That's why I react with that carbon rather than with that oxygen on the acetone. It's all about polarity. And now we see we've already brought in like half of Chem 105, and we're like 4 lectures deep. So this is good. But that's something that we can also use to predict our chemistry. Yeah?
You might have just said this, but the electrons from the pi bond that went to the oxygen that gave us a negative charge, is that just because it's more electronegative? So they tend to be here?
So yeah, the question is, so when these electrons push up onto the oxygen, so like right here, do they go up because the oxygen is more electronegative? Is that correct? So the electronegativities, that partial positive, partial negative, is going to tell us where is the OH minus coming in? Where is that attacking? That's determined by the electronegativities. Now, as far as the arrow pushing right here, that's more of a result of the fact that we can only have 4 bonds on our carbon. Those electrons have to go somewhere. And since it's a pi bond that's being shared between the 2 electrons, they're just going to go to the other atom. Now, therefore, roundabout, yeah, it's because of the electronegativities. But the electronegativity is pushing the reaction, and then the arrow pushing is following suit, is how I would say that.
And here is the other clue, and this is why this is so cool. And it is, you have to break the pi bond when you do this, not only because you'd have too many bonds to carbon if you didn't, but because what is the identity of your LUMO? It is the pi star. You fill an antibonding orbital, you break a bond. That's general, that's always. Does that make your brain go? Like the first arrow is the first arrow from the oxygen to the carbon is the homo attacks LUMO arrow. But then the second arrow, the black arrow going from the pi bond up to the oxygen, that's what's predicted by knowing what the LUMO is. It's an antibonding orbital, so the bond has to break. And if you go up to the example that Nate did previously with the carbocation, notice the LUMO there, not an antibonding orbital, right? So there's no second arrow. You just need one. The first arrow makes the bond, nothing else happens. So the identity of your LUMO determines what else happens after homo attacks LUMO. That's kind of cool.
Yeah, thank you. Yeah?
Just in general, when it comes to the arrow mechanisms, just doing one arrow would be fine, or how do you need to convey like the transfer of electrons, say if you break that carbon oxygen?
Good question. So I got to show all of my electrons moving somewhere. If my molecule changes, I have to show an arrow showing that. So what I've done in my product, and by the way, the question was, how many arrows do I need to draw? So in here I see, in my final product compared to my reactants, I've created this bond, and I've changed that pi bond into a sigma, or to just a sigma, and an extra lone pair. So I got to show that. I'm going to show this bond being created, and then I'm going to show that those pi electrons moving into a sigma to be a lone pair.
Just to be clear, will you erase the wrong arrow?
Oh, yes, I will erase the wrong arrow. There we go. Those are the arrows I would need to draw. Okay. All right, so I've got a couple minutes. I've already taken all of Dr. Price's time that he was going to take.
You can't shut me up. Knock yourself out.
Yeah, so we've got one more example. And this one is very, very similar to question 3 on your quiz. So you will be able to answer question 3 after seeing this example. So we're going to see H3CS minus plus H3Ci. And I'll draw those lone pairs on there as well for completion's sake. So once again, let's identify our HOMO and our LUMO. So on the sulfur-containing molecule, my HOMO is going to be my lone pair on sulfur. And my LUMO is going to be something. It's not on my list. So I'm just going to leave that as a question mark. Probably some sigma star, but it's not something important. On the other molecule, my HOMO is going to be a lone pair on iodine. And my LUMO is going to be a sigma star between the C and the I. Remember, those were the sigma stars we care about when we're bonded to something interesting, when we've got a weak bond. So iodine being such a massive atom, it doesn't really care about making bonds. So the carbon-iodine bond is very weak. So I've got an important HOMO on the sulfur. I've got an important HOMO and LUMO on the iodine compound. That tells me what's going to happen. My HOMO is going to attack my LUMO in the only way that I can see that occur. And so I can push my arrows. My lone pair on my sulfur is going to come and attack this sigma star, and that is going to give me this as a product. And what I encourage you to do over the weekend, what I encourage you to ponder, is why we would get this as the result. So we're going to boot off that iodine, get an I minus, and create this product. So ponder over the weekend why that was the case.
On your way out, leave the quizzes. They don't have to be done. This is just getting credit for the learning exercise.